So here we have an inelastic collision featuring a mass of 1,000 kilograms traveling at 9 meters per second and a mass of 2,000 kilograms traveling at -3 meters per second. It's an inelastic collision, therefore the two masses stick together and have one final velocity. So using the equation for inelastic collisions, we solve for the final velocity, which is the thing that we do not have, and we get 1 meters per second. So here is the car and the truck after having collided, and they're traveling at 1 meter per second. With this information, we can determine the change in kinetic energy. So the first thing we do is we find the initial kinetic energy by summing the kinetic energies of the two masses before the collision. So we have 1/2 mv squared of the mass 1 and 1/2 mv squared of mass 2. When we plug in all the numbers, the 1,000 kilograms and traveling at 9 meters per second and the 2,000 kilograms traveling at -3 meters per second, we get 49,500 joules of energy. When solving for the final kinetic energy, we use the final velocity that we determined for after the collision, and we plug in both the masses because they become one mass. So we have 1/2 ma plus mb times the final velocity squared, and we have 1/2 30,000 kilograms times that 1 meter per second squared, and we get 1,500 joules of energy. To find the change in kinetic energy, we subtract the final kinetic energy from the initial kinetic energy, and we get 48,000 joules. 74 kilogram Logan, traveling at 7.6 meters per second, just lost his balance after making a layup, and in 0.16 seconds he collides with a wall. In this equation, we are supposed to solve for the force, the magnitude of the force acting on Logan's body. We will use the equation that says the impulse equals the change in momentum. We know that force times the change in time equals mass times the change in velocity. So we're going to solve for the force because that's what we're looking for, and by rearranging the variables, and then we're going to plug everything in. So we know that he's 74 kilograms, and he's traveling at 7.6 meters per second, and it takes him 0.16 seconds. We're going to plug in all those numbers, and we're going to get 3,515 newtons of force acting on Logan's body. So in this equation, a pitcher full of cola is being slid across a counter over a distance of 0.48 meters. The mass of the pitcher is 2.6 kilograms, and the force applied on the pitcher is 8.8 newtons. Here's a picture showing the 8.8 newtons being applied to the 2.6 kilogram pitcher as it travels 0.48 meters. Here's the free body diagram that shows that the forces in the y direction cancel out because they equal one another. F normal on the pitcher by the counter equals F grav on the pitcher by the entire Earth. The forces in the x direction, however, are not equal. F applied on the pitcher by Pete is greater than the friction on the pitcher by the surface. So when summing the forces, we know that F in the y direction cancels out and that becomes 0. So F net is just F in the x direction, which is F applied minus friction. Using the numbers given, we can actually solve for friction because we know that friction equals the coefficient of friction times Fn, and Fn also equals mass times gravity, which also equals the force of gravity. So we plug in those numbers and we get 7.13 newtons. As I said before, F net is F applied minus friction, so F net is 8.8 newtons minus 7.13 newtons, which we just calculated as friction, and we get that F net equals 1.67 newtons. To solve for the final velocity of the pitcher, we're going to use the equation that for work that says that F net times delta x equals delta k, which is the change in kinetic energy. The change in kinetic energy in this equation says that the velocity initial is actually a number, whereas velocity final is 0 because it slows to a stop. So we just need to find the velocity initial. We have F net, we have delta x, and we have the mass, so all we have to do is solve for the velocity by rearranging the variables. And we get the velocity equals the square root of 2 times F net times delta x over m. We plug in the numbers, we get 2 times 1.67 newtons, which was the F net. We have that times 0.48 meters, all over 2.6 kilograms, which is the mass of the pitcher. Our velocity initial comes out to be 0.79 meters per second. In this equation, Dagan places a brick on a wooden board and inclines the board at 24 degrees above the table. The coefficient of friction between the brick and the board is 0.328. We're being asked to determine the magnitude of the brick's acceleration. The first thing we need to recognize is that the force of gravity is being split in the x direction and in the y direction. The normal force is equal to the force of gravity in the y direction, which equals mg cosine theta. We know this because the cosine of an angle is the adjacent side. So when summing the forces, we recognize that the normal force minus the force of gravity in the y direction equals 0, which means that F net is going to equal the forces in the x direction. So the force of gravity in the x direction minus friction is F net, which is what it says here. And that equals ma. F net equals ma. Well, we're going to solve for acceleration, so we're going to set a equal to F net over m. So now what we need to do is determine what the force of gravity in the x direction is and what the force of friction is in this equation. Well, the force of gravity in the x direction is mg sine theta because of SOHCAHTOA. It's the opposite side from the angle. And then friction is the coefficient of friction times the normal force. Well, we already determined the normal force is mg cosine theta. So the force of friction is the coefficient of friction times mg cosine theta. Well, we plug those back into the equation. Acceleration equals the net force divided by mass, and we get mg sine theta minus the coefficient of friction times mg cosine theta all over the mass. Well, the mass cancels throughout, so we're left with acceleration equals gravity times sine theta minus the coefficient of friction times gravity times cosine theta. We're now going to plug in all the information that we have, and we're going to get that acceleration equals 9.8 meters per second squared times sine of 24, which is the force of gravity in the x direction, minus 0.328 times 9.8 meters per second squared times the cosine of 24, which is our friction force. And when we subtract those two, we get that the acceleration is 1.05 meters per second squared. And that is the magnitude of the brick's acceleration in this equation.